So in this video, we are going to solve problems from exercise 12.2, which belongs to chapter number 12, Heron's formula. So let's look at question number 1. So let's bring it in the focus. Yes, let's read it out. A park in the shape of quadrilateral ABCD, okay, has angle C as 90 degree, and AB is 9 meters, BC is 12 meters, CD is 5 meters, AD is 9 meters. How much area does this occupy? Okay, so the key thing that is given to us is it's a quadrilateral ABCD with C as 90 degree. So let's try to draw a quadrilateral first. Okay, with C as 90 degree. So something like this, and yeah, okay. So let me try to erase this. Okay, cool. So okay, so now we have, so angle C here is 90 degree, so that is an important part. Then let's put here as B, let's put this as A, let's put this as D. Okay, now the measures of each side is given to us. So AB is 9 meter, so let's note it down. AB is 9 meters, BC is 12, so BC is 12, then CD is 5, then CD is 5, and AD is 8. Okay, so we know that this is now a quadrilateral, okay, with all the four sides given to us, and we have to find the area. How much area does it occupy? We have to find the area of this quadrilateral. So what we are going to do is we are going to apply Heron's formula to this quadrilateral to find the area. Now we all know in order to apply Heron's formula, we need to first have a triangle with all the three sides length known to us. So let's construct the diagonal BD. Okay, by constructing this diagonal BD, yes, we can see we have two triangles here. Okay, and we can find the area of this triangle, area of this triangle, add it up, and that will give us the area of the entire quadrilateral. Now, in order to find the areas of triangle, we should know the length of all the three sides, but the length of side BD is not known to us. So our first task will be, I'm going to note it down. First task is to find length. Okay, find the length of BD. So we have to find the length of BD. That is our first task. How are we going to do it? So first of all, let me highlight it. So yes, so this is our triangle BCD, and we are given key information that angle C is 90 degree. If angle C is 90 degree, then in this right angle triangle, we can use the Pythagoras theorem. Okay, quite simple and straightforward. So using sorry using Pythagoras Pythagoras theorem for, okay, right angle triangle. I'm going to write it explicitly. For right angled triangle BCD. Okay, what is the Pythagoras theorem? It will be BD square is equal to BC square plus CD square. Okay, basically hypotenuse square is equal to the summation of other two side square. And what is hypotenuse? Hypotenuse is the side which is opposite to the right angle triangle. Okay, so now let us substitute the values. So BD square is as it is, BD square, that is equal to 12 square plus 5 square. Okay, now let's focus on this and solve this. So this is equal to 144 plus 25, that is equal to 961. So BD square is equal to 169, and therefore BD is going to be under root of 169, and that is equal to 13. Okay, in fact it's going to be 13 meters because the unit is given to be meters in the problem itself. So yes, you can say this is meters, everything is meters. So we have found out the length of BD. Here it is. BD is 13 meters. So let's zoom in here and note down the length of BD. So I'm going to write it here, 13 meters as the length of the BD. Let's try to erase this highlighted thing. Okay. Now, once again, let's have a look at this quadrilateral of ours. In this quadrilateral, we have two triangles now. One is BCD, one is ABD, and in both the triangles, we know the length of all the three sides. So we can easily use the Heron's formula to find the area of both of these triangles. Okay, so we're going to start with triangle BCD. So once again, okay, let us create a copy of this so that we can use it ahead. the okay, copy, and let's come down. Yeah, we have a lot of space here. Paste. Okay, so this is our quadrilateral here. Now let's try to zoom in. Okay, so first step, let us find the area of triangle BCD. Okay, let's try to highlight it. So BCD is one triangle. Let's find its area. So okay, area of BCD, area of triangle BCD is equal to, now we can find the area of triangle BCD using Heron's formula because we know all the three sides of the triangle. However, BCD is also a right angle triangle, which means if this is the height of my triangle, then this is the base of my triangle. So instead of using a Heron's formula, which is a bit complicated and a time consuming process, let's use a simple formula, which is half into base into height. Okay, you know that area of all triangle is equal to half into base into height. So in case of BCD, it is base will be CD and height will be BC. That is equal to half into, what is CD? CD is 5. What is BC? BC is 12. So that is equal to 5 into 6. Okay, and that is equal to 30 meter square. 30 meter square is becomes the area of triangle BCD. Okay, very important. I'm going to repeat again. The reason we are using this formula in this triangle is half into base into height. Why are we able to use this formula here? Because C is 90 degree, which means this is the height of my triangle and this is the base of my triangle. We cannot use this in general for any other triangles because usually the height is not known to us because the triangles won't be right angle triangle. So this was a kind of a rare scenario where it was a right angle triangle and hence we could use this formula, half into base into height. No need to use Heron's formula. However, even if you use Heron's formula, you are going to get the same answer, 30 meter square. So this is 30. I'm just going to make a note here. Okay, so I'm just going to write here, this is 30 meters square. Okay, now let's go ahead and focus on the other triangle, which is ABD. So once again, let's get rid of this. Okay, now let's highlight the triangle ABD. Now for triangle ABD, yes. Now for this triangle ABD, there is no, we cannot use the formula half into base into height because we don't know the height, measure of the altitude or measure of the height for the triangle. So we have to use the Heron's formula. So using, okay, Heron's formula, okay, how do we use Heron's formula? Step number one is we find the value of variable S. S is equal to A plus B plus C the whole divided by 2, where what is ABC? ABC are the length of the three sides of a triangle. Okay, this thing. So let's just substitute it. So that is going to be equal to, let's say, 9 plus 13 plus 8 the whole divided by 2. That is equal to, what is 13 plus 9 is 22. 22 plus 8 is 30. This is 30 divided by 2, which is equal to 15. Okay, so therefore the value of S is equal to 15. So this is the first step in Heron's formula. And in second step, we say we directly find the area. Therefore, area of triangle ABD, okay, is equal to what? So this is the formula, S into S minus A into S minus B into S minus C, and it's the square root of this whole thing. Okay, so square root of this whole thing. This is the standard Heron's formula. Now we are going to substitute the values of S, A, B, C for this particular triangle that we are focusing on. So the value of S is 15 and A, B, C is 9, 13 and 8, the sides of a triangle. So let's put these values. So here we are. This will be equal to square root of S is 15 into 15 minus 9, okay, 15 minus 13 and 15 minus 8. So sorry. So these are the three sides of a triangle and this is our square root sign. Okay, so that is equal to square root of, let's come down here. Okay, so we have 15 into 15 minus 9 is 6 into 15 minus 3 is 2 into 15 minus 8 is 7. So square root of this whole thing is going to be the area of our triangle. Now let us try to see if we can optimize something. So this is 2, this is 3 into 2, this is 5 into 3, so 7 into 5, 35. Okay, so let's try to split it up. So 15 can be written as 3 into 5. Okay, I'm just going to highlight for understanding. This is 15, this is 3 into 5. Then 6 can be written as 2 into 3. So 6 will be, okay, 3 into 2. Then 2 will be as it is and 7 will be as it is. Okay, now that is equal to, as we can see, there are two threes here. Okay, so we'll just group them. So 3 into 3, okay, into 5, or okay, let's keep 5 later on, into 2 into 2 into 5 into 7, and square root of this whole thing. Okay, nothing special. I have just rearranged the terms for easier calculation. So this 3 and this 3, they have come together, and this 2 and this 2, they have come together, and 5 and 7 have come here together. Okay, now we know square root of 3. Okay, so this whole square, sorry, so this whole square root operation will be applied to each of these terms. Okay, so let's continue. So this is going to be square root of 3 into 3, which will be 3. Then it will be square root of 2 into 2, which will be 2. And then it will be square root of 35. Okay, so that is going to be 3 into 2 into square root of 35. I will keep as it is. So square root of 36 is 6, exact perfect square root. Square 36 is a perfect square root number, but 35 is not, so it will be 5.9, 5.95, something like that. So no worries, we'll keep this value root 35 as it is. So we can write this as 6 into root of 35, and that is our meter square. Okay, that is the term, sorry, that is the unit. Meter square is the area of this triangle, 6 root 35. Which triangle? This triangle ABD, this one, triangle ABD that we are looking. So let's come here. This was our original figure. So it's going to be 6 into root of 35, okay, meter square. So we now have area of this triangle, we have area of this triangle. So finally, when they're asking us how much area does this occupy, the whole quadrilateral ABCD, so it's going to be this term plus this term. So I'm just going to write it here. It is going to be 30 plus 6 under root 35. Okay, and you can just put a bracket and say this meter square. This becomes the area of the quadrilateral ABCD. Thus, we can see that we have used Heron's formula. This is an interesting application of Heron's formula to find the area of a quadrilateral where the sides of the triangle are given to us. Sorry, sides of the quadrilateral are given to us. That's it.